Hello, in today's video we're going to be talking about the van der Waals equation. This equation takes our ideal gas law and kind of manipulates it in such a way where we can account for some of the more realistic aspects of gases. So when we were talking about ideal gases, we know that it was a good predictor of the way gases move if they're small and if they're moving at a very high temperature or high speed. What happens when we start slowing them down and making them bigger? Increasing the pressure and as well as making them bigger. That's in effect what we're doing. Well, we have to put in new terms into our equation, into our ideal gas law, in order to identify and account for these changes of the real gases. So let's write up the ideal gas law, PV equals nRT. And let's see what really happens. In the ideal gas, there's no interaction between the molecules. So a particle of helium doesn't see another particle of helium. They're moving around each other. There's no interactions. That doesn't really happen in real gases. If we have a cylinder where we have two particles, one's moving up, one's moving down, so this one is moving down, this one's moving up, as they pass each other, their intermolecular forces actually act on each other. And so this particle is either attracted to or repelled from this particle. It changes the direction of this particle. I've said earlier that in ideal gases, the particles move in straight lines. Well, in real gases, they don't. The particles are kind of shifting around as if there's a gravitational field around each of the other particles. So there's this intermolecular interaction going on here. That changes the pressure of the system. As this particle is trying to hit this wall on the right, it feels the forces of all of the other particles in the beaker. That actually slows down the particle trying to hit the wall. And we know that pressure is the amount of force per area. That's what the definition of pressure is. So if this particle starts hitting the walls with less force, it means that the pressure has gone down. So we have to do a corrective term to the pressure. So that's the first term we're gonna correct for. The second term is this volume. As we have, we generally think of gases are very, very small, and so the actual size of the particle doesn't affect the overall pressure of the system. We don't account for that. While in real gases, if we have an extremely high pressures, the size of each of the molecules starts to play a bigger and bigger role. And so what that means is we're going to have to account for this volume change. If we have a very small beaker and a relatively large particle, the free space, the space that this particle is allowed to travel, actually is reduced compared to if we had a large beaker. This will become more apparent as we do some of these examples. So we're going to have to write something different for the volume as well. So let's start off with our ideal gas again. So those are the two interactions that we're going to have to account for. The pressure is going to be slightly different and the volume is going to be slightly different. So ideal gas is this. For our van der Waals equation, which treats real gases, we have a new equation. The pressure has been changed to a new pressure that you're going to end up adding a term to over V squared. Where our new pressure is now, we're going to add to it mole squared times A. A is a constant. It's found in a table, page 216 of your textbook. I will give you the A's and B's on an exam. And then we're going to divide that by the volume squared. So this is our new pressure term. Our new volume term is going to have something similar to this. We're going to have the original volume, and we're going to subtract a term from that, NB. The amount of moles of gas times B, which is another constant found on page 216 of your textbook. The right-hand side is actually the same. This equation right here is our new van der Waals equation. So this is how we're going to treat real gases. And this equation up here is our ideal gas. So this is ideal. This is real. Both of them identify, and we can calculate pressure from both of them. This one's slightly more difficult So what I said at the beginning of the semester is we're going to have an equation that has 7 variables, 1, 2, 3, 4, 5, 6. Okay, so there's only 6 variables and 1 constant. So this equation, we're going to have to be able to manipulate in order to identify the pressure or the volume or the moles. So it gets kind of tricky. There's a lot of algebra that can go on here. So let's do a simple experiment. Let's say that we have CO2 gas, and I'm going to give you some of the constants, and we're going to identify what the ideal gas law says the pressure should be, and what the real gas law says the pressure should be. So CO2, we're going to say it's at 299 Kelvin, it's at 1.98 liters, and there are 4.89 moles of the gas. Let's first take the ideal gas law and plug in our values. So the real gas law I'll rewrite when we're trying to figure that out. And let's say that in laboratory we actually measured the pressure of this system, and we found that the pressure real is going to be, 44.8 atmospheres. So this is what really happens in laboratory. I want to show you what the 2 different equations give us, what pressures they give us. So we can rearrange this equation to give you pressure is equal to nRT over V. We plug in all of our values. We have N is 4.89 moles. We have R, which is 0.0821 liters atmospheres per mole Kelvin. And we have the temperature of 299 Kelvin. We're going to divide all of that by the volume, which is 1.98 liters. And if we plug this into a calculator, we end up getting a pressure of 60.6 atmospheres. The ideal gas law predicts that our pressure is going to be 60.6 atmospheres. We know in reality, we performed this experiment in lab, that our pressure is 44.8 atmospheres. Big difference. So pressure ideal is going to be 60.6 atmospheres. So now I'm going to erase all this. I only have so much room on this board, so sorry about that. And I'm going to rewrite up our gas law, our van der Waals equation. Pressure plus AN squared, or NA squared, over V squared times V minus MB is equal to nRT. Now we have to solve this equation for pressure, slightly more difficult. Pressure is going to be equal to nRT over V minus NB minus AN squared over V squared. So really all I did was algebra. I divided this by both sides, I subtracted this term from both sides, and I get this equation. Now I'm not going to write out all of the numbers here. You can input those. But I will tell you, if you look up on page 216 of your textbook, the value A for carbon dioxide is 3.59 atmospheres liters squared per mole squared. Kind of a weird unit. And B is 0.0427 liters atmospheres. Okay. So these are our term A, and this is our term B. You can plug in all of these numbers down here, and what we end up getting is a pressure of 45.9 atmospheres. Much, much better than our ideal gas law. So the pressure van der Waals is going to be 45.9 atmospheres. You can see that the real pressure is 44.8 atmospheres. The ideal gas law predicted 60.6 atmospheres, and the van der Waals equation predicted 45.9. These two are much closer together. The van der Waals which treats it as a real gas, actually predicts the pressure better than the ideal gas law. And with that, I want to end this example. We're going to perform a lot of these examples in class tomorrow. The van der Waals equation talks about real gases. The ideal gases talk about ideal gases. So you're going to have to read the problem in order to understand if it's an ideal gas or a real gas. and then we can predict different properties using tables in their textbook or information that's given. So with that, I want to say have a great night. I will see you all in class tomorrow.